Buongiorno a tutti. Welcome everybody. Can you hear me? Well, welcome to this lesson of the course Three-Dimensional Digitization. Today there will be a workshop based on photogrammetry, and Carlos Bayod and Otto Lowe will hold this workshop. Thank you for being here. This course is, of course, going to last other 2 lessons that will be, again, 1 class and 1 workshop. I think I will leave the floor directly to Carlos and Otto. Thank you.
Thank you, Constanza. Can you hear me?
Yes, very well.
Thank you for the introduction, and thank you everyone for attending the session. I will share my screen now. Can you see it?
Yes.
Okay, so welcome to the 3D course, and today is going to be a workshop. It's going to be more practical, and we will try to get into detail about the technical aspects of photogrammetry, and we will be doing it with the approach of photogrammetry that we follow in the Factum Foundation, which is focused on close range recording, focusing on trying to capture not only the general shape of things, but also the actual detail on the surface. And for this introduction, I am today with Otto Lowe. Otto is responsible for many projects about 3D recording and especially photogrammetry in the Factum Foundation. And that means that there's probably he hasn't done any easy project in the last years, because we are always trying to challenge what is possible to do with this technology. So he's been in charge of projects about recording entire landscape areas, for example, entire monumental sites, as well as other projects which were mostly about macro and very detailed photogrammetric recording of small objects with a lot of small details. So he has been in charge of all stages of projects, from selecting equipment, from planning the recording strategies, and of course carrying out the work on the field and then processing the information. So it is a good opportunity that he can explain today his experience and share with us what is how it is special, what is special in the fact of recording with photogrammetry objects of cultural heritage. But first I want to do a quick overview into the relation between the digital information that we capture and the type of prototyping fabrication that we can generate out of it. There is always this idea that the work that we're doing is this two-way trip. It's all about how to transfer information from the virtual to the material. And this is why yesterday I was showing a series of projects in which it was necessary to combine different recording methods, so that for complex recording projects, it is always about how you select the right recording system for each specific artifact. So throughout the process of creating a facsimile, these different steps of mediating information are completely related to each other. So from the phase of input, which is the actual recording of an original object, and then until you process the information and you fabricate it and you actually remake it physical again through prototyping, there is a series of steps that are necessary to take into account. And I would like to show what is the relation between the system you have used for recording something and then the system you choose for fabricating it. That means that what is the ideal output system for each for its correspondent input technology. So the different output systems, or we can call it digital fabrication methodologies, we are mostly focused on those techniques that can give us a lot of information in the surface detail, focused on being able to produce high resolution artifacts, so that the data that we have captured with our high resolution scanners can demonstrate, it can be rematerialized with the right level of information. We are usually dividing the fabrication systems in two groups. Mostly this differentiation between subtractive technology and additive technology is what is very common today, not only in our field, not only in cultural heritage reproduction, but in the industry in general. The idea of subtractive fabrication is what we can consider the traditional method of making things, also for craft techniques, not only in the industrial sector. So it's about creating a tool, creating a shape, creating a design out of removing the extra material that you don't want, starting from a block, from a solid block of material. So this is what has been happening in history, in all sorts of industry, all sorts of ways of making things. Nowadays, it's becoming also important to consider additive manufacturing techniques, which is what we are commonly referring to as 3D printing, which effectively the concept is in a way the opposite. Instead of removing the material that you don't need to generate the shape that you are looking for, what you do is adding only the material that is required to actually generate your design or your shape or your model. Basically, it works as adding layers of material. So it could be considered in a way more sustainable, because you are not wasting any material. You are only using the exact material that you need to generate your shape. I will show you examples of each of these techniques, and especially how we use them in the Factum Foundation, and what are the advantages and disadvantages of each of these groups of fabrication techniques. From the things that I've been showing in the last sessions, mostly everything that has to do with subtractive fabrication is, for example, the CNC milling machines, the CNC routing, which is exactly what you can see on the screen right now. It's this tooling that is removing material until you generate the texture that you want to reproduce. On the other hand, 3D printing is the best example of this idea of additive fabrication. But there are many different methods, different approaches to 3D printing, which can give us specific results for what we are looking for. So I chose these examples, which is the most common techniques we are using. And to begin with the subtractive fabrication techniques, I would like to focus for one moment in computer numerical control milling. This is basically the idea of sending a series of commands to the machine to actually generate a series of movements, a series of orders that are necessary to rematerialize a 3D model or any sort of 3D information that you have previously in digital form. So basically what you need is to transfer the information in CAD software into CAM software. So it's going from the digital information to the physical rematerialization of data through this translation of information. Normally, we can use 3D data in different formats, different file formats. One typical way of understanding 3D shape is, for example, the STL format, which is basically a 3D mesh. It's basically a way of having all the points that conform a 3D model joined together through a series of polygons. Yeah, and then another way of actually, a very efficient way of working with 3D information is when we are using a depth map. So in a way, a depth map is an image file. It can be, for example, a TIFF file that contains information of depths and heights through different tones of gray. Depending on the project, we are looking for one way or the other to use 3D information. But normally when we are working with 3-axis routing machines, we prefer to go for 3D information as a grayscale depth map format, because it's facilitating the work of the machine, and it's also not necessary to use such big files for having the same amount of resolution, the same amount of information. So this is a 3-axis routing machine because it moves in the X, Y, and Z direction. And what we are doing is milling from a block of material that is basically a flat block of material. But then there are also multiple axis machines, milling machines, especially defined to generate volumetric shapes. So the tool is actually carving the block of material from many directions, not only in terms of depth and height. You select the tools or the bits depending on the diameter, the shape of the bit, and then depending on the material, you will be able to obtain a higher or lower resolution, which means a higher or lower level of detail. When you want to recreate very fine detail, a lot of information of the surface, you should try to go for high density materials, for example, polyurethane resin panels. But then if you are just interested on generating a very basic shape, not interested on the actual quality of the surface, you can go with using just lower density materials like these ones. When working with a 3-axis milling machine, it's all about carving the material from the top. So there is usually a maximum thickness that you can actually use for generating your relief. Whereas when you are operating with a multiple axis milling machine, it's all about the block of material that you will be cutting from the different directions. I showed you this example in previous classes, and this is the render. This is a shaded render of one of the objects that we have recorded with the Lucide scanner. This is the Hereford Mapamundi. This is the visualization of the relief through an image. So this is actually a way of understanding the texture through a virtual shaded image. The correspondent grayscale depth map of this file looks like this. So it's basically a gradient of grays, of tones that are effectively understood by the milling machine as differences in height. And then, especially if we were looking closer, if we were doing a zoom into this file, which is actually an image file, we would see that each pixel contains a specific level of gray, so that the machine will do its correspondent carving according to the level, according to the tone. This is the relation between tone and relief that we are constantly working around, and we are constantly experimenting with in Factum. The correspondence between tone and relief is very simple, especially when you are working with translucent materials like this one. This is just a toy. This is a very simple example of something that, because it's translucent, depending on the thickness of the material, it is allowing more or less light through it. So this very simple toy that probably came in a cereal box or something, it's in a way very sophisticated in how it is generating an image, a tonal image, out of the different thicknesses of the plastic. Taking this idea, it is how we are working in many of the projects that we do, not only related to cultural heritage, but also related to contemporary art. It is helping us to understand this relation between tonal information and relief information. Some years ago, we started a collaboration with artist Marina Abramovic, and we tried to play with this idea. So starting with black and white photographs, just black and white images of her with specific gestures, with specific faces, we were trying to use this tonal information of the black and white images and translating them into relief information. So taking a block of alabaster, which is a translucent stone, we were carving the different depths according to the different tones of gray in the image. This is not coming from a 3D scanner. This is not like we were 3D scanning her or her face. It was just a translation from a black and white image into a carved relief in a stone like alabaster. So when you have light from behind, suddenly the image appears. But when you are not having the object with light from behind, what you find is something that is kind of abstract, like a landscape, something that is not easy for recognizing an image on it. We created a series of editions, a series of variations on this theme for her, and it has resulted in a very interesting series of works because it has allowed us to experiment with different materials, with different thickness, different levels of approaching this relation between tone and relief. And at the end, we could give an answer to what the artist wanted to do, because Marina Abramovic, as you know, she's famous for being a performance artist. She wanted to create something that could be more permanent, more solid. And then for that idea, working with stone was evident and was something that would work very well. But at the same time, she wanted something that was solid and permanent, but at the same time with a feeling of impermanence, with a feeling of being ethereal, so that her image could appear and disappear depending on subjective factors, like where the person is positioned in relation to the object, or in relation to whether there is a certain amount of light. So at the end, this type of object and this type of technique could give an answer to all of these requirements about creating something permanent and ephemeral at the same time. So this relation between tone and relief is very evident, and we are using it in many of the techniques for recording and reproducing information. If we jump to another type of fabrication techniques, if we talk now about additive fabrication techniques, basically types of 3D printing, one of the most basic examples is this idea of the fused deposition modeling, which is basically the most, let's say, inexpensive and available 3D printing machines that have been appearing quite a few years earlier. And it's all about starting from a roll of thread, just like a filament that is thermosensitive. So when it's applying heat, it is possible to melt it and then convert it in liquid that solidifies quickly as you are creating your layer of material. So just a few diagrams of how this technology specifically works. So once you have your 3D model that you want to generate, any design, any 3D shape that you want, this machine, what it's doing is understanding the piece as a series of, as a stacking of layers. So you are building, as if you were drawing in space, the shape with this filament that, because of the heat, becomes liquid, and then it can become solid again just after a few seconds. What you obtain is a shape that corresponds exactly to the 3D model that you have in your computer. And then it is possible also, if the shape requires it, to 3D print as well a kind of supporting structure, like a kind of scaffolding that helps to keep the integrity of the piece as it is being built. This structuring support, it can be removed mechanically at the end of the process. And this is the technique that has been, for example, made popular through brands like MakerBot that were offering machines, like desktop machines like this, to create small parts or small pieces that you can design at home, and then you can build in your own small 3D printer. But this is usually not giving enough resolution in the surface detail. You want to go to other methods of 3D printing if you are interested on reproducing not only a design or a prototype of a shape, but also if you are interested in reproducing surface texture. Other ways of 3D printing or additive digital fabrication is, for example, laser sintering, which is basically, instead of starting with a filament that you are heating, what happens is that you start from a powder material that also, with temperature, it can get solidified only in certain areas where you are defining your shape. So starting with specific powder that is thermosensitive, you can build your layers as you are bringing down your volume of powder. So at the end, you extract your solid piece out of this bed of powder. In this case, the actual powder itself can act as a structural support. So there's no need to build other additional scaffolding as part of your 3D printing. You just have to remove the extra powder. And examples of this, kind of more experimental, have been, for example, this idea of fusing the sand in the desert. So with the actual material that you can find around, just by focusing, for instance, solar power, and through that you can generate your solid layers and then create any material that you want. But this is like experiments about testing what is possible and what should be possible to be done in the future with 3D printing out of the materials that you have, that you can find in the environment. And finally, the real 3D printing technique that we are constantly using because of the surface quality that it offers is stereolithography. And in this case, what you are doing is solidifying from a liquid. So you are starting from a kind of transparent liquid resin that you can solidify with a UV laser only in the points, only in the areas that you want. You start from the liquid, and the 3D printing machine, what it's doing is solidifying layers. So at the end, you bring your solid piece out of this bucket of liquid material. Very quickly, I want to show a couple examples of how we are using this stereolithography technique. For example, the project of recording and reproducing the Cellini bell. It's a very good example because for rematerializing this object, which is a very tiny bell, it's about 10 centimeters high, it's made in silver. It's one of the great examples of this decorative way of from the 16th century. This original piece is in the British Museum. So we had the project of recording this, and this is actually something that my colleague Otto was in charge of doing. So he would be better prepared for explaining this if he wants. But basically, the recording of an object like this with photogrammetry required a very complex approach in which it was necessary to capture the object in two steps, one of them being using cross-polarizing filters as a way to filter the excessive glare or the excessive reflections from the material, and then being able to merge together as part of the processing these two sets of data, so you could be using the best quality photographic information for generating your 3D model. Otto will explain us more in detail all this process between capturing your photographs until you generate your 3D model. But in this case, it was about almost like an exercise of macro photogrammetry, because it was necessary to be able to capture every single detail that you can see in the 3D model that was resulting of this recording. Every single detail of the bell needed to be present in the 3D model without any simplification. All the complexity of the object should be there in the digital model, so that when we rematerialized it through stereolithography, it was perfectly correspondent to the level of character of the original element. This is the result of reproducing at real size the Cellini bell that was recorded with photogrammetry. And this is a picture of the final reproduction that we did, also with a silver finishing. And if you put it side by side with the original, you could tell that all the details are actually there. And this was possible thanks to this complex recording method that I just briefly mentioned, but also thanks to the stereolithography 3D printing technique that made it possible. I want to show another example of applying 3D printing. This is a 3D scanner that we created in Factum. It's called the Veronica scanner, and it was designed in order to capture the faces and the heads of people in 3 dimensions. The way it works is through photogrammetry. So having the person in the middle of this sphere, there is like an arch containing a total of 10 cameras that are making a 360 turn only in a couple seconds, and they are coordinated to shoot every time they pass through these holes in the sphere. As a result of this simple mechanism, what you obtain is 100 photographs of the face of the person from different points of view. And this is actually the principle of photogrammetry, is how you obtain 3D information out of taking multiple photographs from different points of view of the same object. This system that we created in Factum, it was meant to be done for making 3D portraits of people without the necessity of having an artist making a sculpture. You can obtain a 3D model of someone with a specific gesture, for example, smiling or shouting or doing any specific movement, because the capture is at the instant. So it's no necessity to be still for a long time. It's something that happens immediately. And the important thing for us is to capture not just the general shape of the head, but also every detail of the surface, as if we were talking about a specific cultural heritage object. When we are trying to record people, it's very important to capture every detail of the skin, all the wrinkles, etc. And this is thanks to the combination of the different images, color images, that give us a result, this level of detail. So the Veronica scanner, it's this photogrammetric scanner that we had on display as part of an exhibition about contemporary portraiture in the Royal Academy in London. And we were showing them, we were actually operating the machine and showing examples of different busts, different 3D portraits that we had created thanks to this recording technique. And we were showing also different smaller 3D printers, so we could recreate small versions of the faces of the people that were being scanned during the exhibition. So people were actually queuing not only to see the show, but also to be recorded in the Veronica scanner. And then we would send them, let's say via email, the 3D model of their faces that was captured with the scanner, but also in some cases we were 3D printing smaller versions of the heads. And when we wanted to print the full size busts, that's when we were in need of using stereolithography, because that's the only way that we could really get to the level of detail we wanted. For large 3D prints, we normally work with the Belgian company Materialize, because they have some of the biggest machines for stereolithography, and they operate in all types of industrial sectors. But when we want to make big sculptures, when we want to make big 3D printed shapes, we work with them because they are giving at the same time big size and very high definition in the surface detail. Working with the artist Mark Quinn, we were in charge of recording different seashells, marine shells, so that we could enlarge them in scale and convert them into bronze sculptures measuring 2 or 3 or 4 meters high. Actually, some of these sculptures were on display on the island of San Giorgio Maggiore in Venice a few years ago, as if they have been left there by the tides, no? by the water in the lagoon. So in order to make objects like this, it is necessary to make sure that the 3D model that you are enlarging contains as much information as possible, so that when you increase the scale, you are not simplifying the information, you are not losing the character of the original. And then for creating the final version in bronze or in any other finishing material, you need to take your 3D print, consider it as your first prototype, and then you can proceed as in any other conventional sculptural process. You can make a silicon mold, and then you can make casts in other materials, as if you were simply going to make a traditional bronze sculpture. Finally, one of the best, one of the 3D printing methods that we are using more often recently is what is called elevated printing. It's a kind of 3D printing that is basically for 2.5 dimensions. This was developed by Otto, which was part of Canon, and we started working with them more than 5 years ago, and now we actually own one of the machines capable of doing this elevated printing fabrication technique. I have shown you examples in the past sessions in which we were using this technique for reproducing the relief of paintings in white, because we are mostly interested on the texture qualities of this technique, not so much in the color. But I want to show you an example of how it is possible to reproduce relief and color at the same time, thanks to this new 3D printing technique. We were recording this painting by Rembrandt, Portrait of an Old Man. And this is a short video that explains the full process.
Carlos, sorry, I'm not sure. I don't hear any sound in this video. Carlos, do you hear me?
Sorry. Yes.
There's no sound in the video.
Sorry. I will go back one moment.
Mm-hmm. Yes, that is perfect.
Thank you.
OC is a Dutch company founded in 1877 and it is now a manufacturer and developer of copiers and printers. When using and testing our printers, we also found out that we could use some of the technology to build layers. We use a flatbed printer that uses ultraviolet curable ink, and the ink cures immediately after printing.
Basically, the technology of elevated printing is stacking ink layers on top of each other. The most challenging were avoiding staircasing and getting the right colors. It starts with the basic layers, and then you already see that it has the correct height. You see the white layer, and slowly you see also the color coming up, and here in the end it's the final print. And what we do is we print layer by layer, and at the moment that we have the right height, we are printing a white layer on top of it, and then we print on color.
So, as you can see, this is a 3D printing technique that is only adding the layers of material that are needed to complete the relief, with the difference that in this case, we can incorporate the color as part of the relief. At this moment, we prefer to use the color and print the color with our own printer. We prefer to have more control over the color finishing. And this is why for making our painting reproductions, for example, we generally use this elevated printing technique only to generate white relief, and then apply the color later at a later stage with another printing methodology. But in this exercise of reproducing the Rembrandt, it was a good exercise to see the possibilities of generating relief and color at the same time. The other project, which is more related to contemporary design or contemporary art, is this collaboration with Jam Jar Flowers in the United Kingdom. In this case, we were recording a series of dry flowers and with the Lucida scanner, as if we were working with a painting. And then, thanks to this technique, it was possible to print very shallow reliefs of these flowers containing all the complexity of the colors and the reliefs. There is a lot of digital mediations involved in making something like this. It is not just about recording something and then pressing a button and it will come out like this. It is necessary a very complex series of steps to make the proper variations and the proper combination between relief information, color data, etc., in order to design something like this. This is basically a design product and not so much something that pretends to be a facsimile. So as a final summary, I would like to make just a general overview between what is the relation between the input technologies and the output technologies. So depending on the original that you have, there is, at least in our experience, a series of recording technologies that are mostly more appropriate for that, and then their corresponding output techniques also that fit better the requirements. So for example, when we are talking about surface objects, I mean, objects like we consider to have 2.5 dimensions, like a painting or a wall relief, as I was showing yesterday, mostly we are trying to use the lucida scanner, but also close range photogrammetry operating in parallel to the surface of the painting or to the surface of the wall. And the obvious methods for reproducing this information is through 3-axis milling fabrication, because that's at the end what you need. It's a matter of having different depths into a system of X, Y, Z coordinates. And then also this method that I just showed you about the elevated printing. On the other hand, if we are working with true volumetric objects like a sculpture or architectural elements, we are not using a lucida scanner, but we are constantly employing white light scanners or structured light scanners, which is the same, or also photogrammetry. As you will see now in Otto's introduction, you will see that it's a very versatile method that can be applied to all sorts of objects, all sorts of shapes, and also different scales and sizes. So when we have recorded 3D form, when we have recorded a volumetric object, the obvious ways of rematerializing that would be to use multiple axis milling machines like these robots I was showing earlier. And of course, the best option nowadays is using one of the different types of 3D printing in order to build this volume, also with the qualities of the surface. So this is based on our experience, and of course there are other methods and other ways of capturing information. But at the end, the important thing that I just would like to communicate is this idea that each original object requires a specific recording method. And then once you have the information, you also have to consider that there is an ideal method of fabrication or prototyping, and which is more appropriate for each type of information. At this moment, I will leave my colleague Otto to present an introduction of photogrammetry, and I will welcome any questions you have about the things I mentioned so far.
Thank you very much.
Any comment, any question? Okay, so Otto, when you want.
Thank you, Carlos. Let me just share my presentation screen. So yes, as Carlos explained, I am Otto Lowe. I am a 3D scanning technician at Factum Foundation, and I run many of the projects, 3D scanning projects that involve photogrammetry. I'll start off by saying that I have no formal training in anything related to 3D scanning. I am pretty much entirely self-taught. And I started with photogrammetry, and I often say that it's the most democratic of all of the scanning systems that we have, in that it's relatively affordable and, at least according to me, relatively easy to learn. So to start off, what is photogrammetry? Well, basically, it's a method of extracting three-dimensional coordinates from two-dimensional images. So essentially what it does is it put very simply, uses trigonometry to determine a distance to a specific point from any two given images. So it's basically mapping features across the images and plotting Cartesian coordinates on a XYZ axis for that specific point. And accumulating millions of points basically gives you a description of a geometry of an object, the shape of an object. It comes from the Greek photos, meaning light, grammos as something drawn, and metros meaning to measure, basically measuring using light. And so for us, it's become a primary tool for digital recording. Because not only is it capable of achieving the required resolution that our projects desire, but at least relatively speaking, it's cheap and it's highly portable. So it requires no special shipping of any large equipment. Usually I travel with just a backpack on a tripod. It's relatively easy to learn if you have enough drive to do so, and more importantly, it's incredibly easy to combine this approach with various other systems. So most commonly with LiDAR scanning systems, but also you can combine it with pretty much anything that produces a point cloud. And on top of this, you can have a variety of outputs from the data. So not just you're not limited to just say depth maps as you are with Lucida, but you can also export OBJs, STLs, PLYs, XYZ, any number of various formats for 3D models. For this reason, it's something that we are very involved in teaching to people around the world. So one of Factum Foundation's goals is to try and democratize 3D recording to local stakeholders in various countries. So one of my projects in recent years has been to train Saudis in the town of Alula in the north of Saudi Arabia to record the rock cut inscriptions and Nabatean tombs that are clustered around their town. So in the pictures on the left, you can see a sort of general training course that I held for, it was roughly 20 people. I think it was 15 women and 5 men in recording rock cut inscriptions in the town of Alula. 2 of these students we brought to Madrid, where they received sort of further training on top of the more general training I gave in Saudi Arabia. They received sort of more in-depth training, and by the end of it, we had them doing a proper project recording the tomb of Cardinal Cisneros in Alcalá de Henares, just outside Madrid. In addition to Saudi Arabia, we've also taught people in Russia and most recently in Somaliland in how to record objects and inscriptions using photogrammetry. And really, as long as you have an understanding of photography, it's relatively easy to pick up and utilize. So photogrammetry is actually quite an old technology. And it's primarily a tool for topographical mapping. So Colonel Aimé Laussedat, apologies if I'm butchering the name, coined the term in 1851. He's often known as the father of photogrammetry, in that it was his theory and sort of designs that were accepted by the Academy of Science in Madrid, which you can see on the bottom right image. Basically his principle of determining points through 2 separate images. Technically it's called stereo photogrammetry because he was then using stereoscopic images. He tried doing aerial mapping by strapping cameras to kites, but wasn't overly successful in doing so. The one who did have a lot of success was Felix Nadar, who's primarily famous for being a portrait photographer, an early portrait photographer and hot air balloon enthusiast, as you can see in the top right image. But he managed to successfully create topographical maps for Emperor Napoleon III in the Franco-Prussian War in 1859. Similarly, the Prussians were actually using stereoscopy, which is similar for mapping French defensive positions. An interesting side note, Nadar was also instituted a sort of air postal service using his sort of fleet of hot air balloons. You can see on the bottom GIF his sort of attempt at doing sort of three-dimensional portraiture using photographs from various different angles of a person. And this is a very similar technology to what we employed in the Veronica scanner. So it's essentially the same as how we scan heads in Factum today. The technology hasn't changed all that much. The only difference between now as opposed to then is that with computers, we're able to map many more points than we were previously. And indeed, people old enough will have studied how to do photogrammetry by hand in a similar way that Nadar and Lowe were doing in the 19th century. So the basic things are involved in understanding how to do photogrammetry is basically knowing photographic terms, photographic theory, and understanding how to take things at the correct exposure. The difference between photogrammetry and general photography is that you're looking at slightly different things. So there's obviously in photography, you have lots of theory about sort of getting certain types of light. Well, in photogrammetry, you actually want the most boring light possible. But you have to understand how to obviously create all of these conditions in order to get the photos right. So one of the first things that it's important to understand is essentially how a camera sensor works. And this will give you an understanding of how to record color specifically, which is a very important part in what we do, an accurate color recording. So a sensor is essentially just something that measures the luminance value of the light hitting each photodiode or pixel. And the way it perceives color is, well, similar to the way our eyes work. It has a series of red, green, and blue filters so that it can measure the amount of red light, green light, and blue light. And these are arrayed in a pattern called a Bayer filter array. There's half of these filters are green because that's how our eyes actually perceive the world. We perceive much more green than we do red or blue. And then the rest are divided between the red and the blue. So the image of the eye that you can see on the left is actually how your camera takes a photograph, how it sees the world. And then this is put through what's called a demosaicing algorithm that basically interpolates the color using basically by measuring the intensities of red, green, or blue in any given area. And so that's how we get color. And each camera company has its own demosaicing algorithm. So each camera brand basically has what's often called their color science. And getting in a sort of, there's no such thing really as objectively true color, but they all look very different because of this different demosaicing algorithm. So it's just something that you have to be aware of. There is one company that makes a different kind of sensor called a foveon sensor, which is basically where the light is filtered through layers of red, green, and blue simultaneously in order to try and achieve true color. But this is a rather niche tool. So the other thing that one always has to bear in mind is sensor sizes. So on YouTube and on the internet, you see a lot of sort of adverts and tutorials on how to do photogrammetry with your phone. and this being a camera that most people have available. And it's true, you can do basic scans with a phone, but in fact, we tend to sort of avoid recommending this as a tool because as you can see from this diagram where you have their relative sizes, the phone sensors are incredibly small. And this means that the pixels are incredibly small and close together and compact, and that can lead to a lot more digital noise. They also use something called computational photography to try and mitigate the size of the sensor, but essentially the sensor is the size of your fingernail. So moving up, you have the micro four thirds sensors, which were quite common in the early days of digital photography. They're the sort of smallest, I would say, professional grade sensors. And then moving up to full frame as the sort of the modern standard. Full frame is sort of harks back to the analog days in that that's just the size that 35mm film was. You also have medium format above this and large format above this. And basically the larger the sensor, the more light it's capable of receiving, which means you can get much cleaner images. They're not subject to quite so much noise. And with photogrammetry, that's what you want. You want to have as much true information as possible and try to mitigate against having any false information or noise, as it's called. You can never totally have a noiseless image, but you want to have as little as possible. So the other thing that's important to talk about is the focal length of the lens that you affix to the camera. So in general, the general rule in photogrammetry is to avoid using zoom lenses, and this is to do with the distortion that occurs between the focal lengths as you zoom through. Each focal length can have different uses. So in fact, we often use the wide-angle lenses for more architectural photogrammetry, and then we use sort of longer lenses for getting very specific details of buildings. But by and large, we try and stick to 50mm lenses if we can, which are sort of a happy medium where the lens carries minimal distortions. So the three important aspects to master exposure are controlling your aperture, your shutter speed, and your ISO. So the aperture is measured in f-stops, or if you're using cinema lenses, they're measured using t-stops. Basically, it describes how tight the diaphragm in the lens is. And the diaphragm basically fulfills the same function as the iris in your eye. And this controls the sharpness and depth of field of your image, which I'll cover in coming slides. The shutter speed is measured in fractions of a second, and this is basically determining how long your sensor is being exposed to light. And so if you have like a shutter speed of 1/500, that's the shutter will be closed for 1/500th of a second. Sorry, it will be open for 1/500th of a second. And then lastly, you have your ISO, which measures the sensitivity of the sensor. Now, the shutter speed and the aperture both have numerical calculations behind their values. The ISO is, despite standing for International Standards Organization, is somewhat less standardized. It's basically inherited from the analog days where you would have it would describe the speed of your film. So you'd have ISO 100 film or ISO 400 film. Nowadays, camera manufacturers tend to use it to measure what their base sensitivity is. So their sort of most noiseless setting will be their base setting, and they'll call that ISO 100. But ISO 100 is not the same between camera sensors. So it's something to be aware of when buying photographic equipment or camera body equipment for doing photogrammetry. So your aperture controlling your depth of field, basically by tightening the diaphragm, you're increasing the depth of field, but you're also letting less light into the camera. So basically you want to get that sort of sweet spot between where the object you're recording is entirely within the depth of field, but the aperture is not, you know, restricting too much light to the camera sensor. So your depth of field also changes depending on your distance to your object. So the closer you are to your object, the smaller your depth of field is going to be, regardless of your aperture. Depth of field refers to how much of the image is in focus. That's not the same as how much of your image is sharp. It should be important to note. So the smaller your aperture is, i.e. the higher the F number is, the more of your image is in focus. But up to a point, there is a point where you get something called lens diffraction, which is basically where the diaphragm is restricting the light to an extent that it's hitting the sensor at undesirable angles. So you can see this on the image to the right, where at f32 everything's quite blurry, and this is subject to because of lens diffraction. So every lens has its kind of sweet spot, as it were, where things are sharp but not blurry, and as much of the image as possible is in focus. And typically with each lens it varies, but typically it's within the f5.6 and f11 range. So usually with your lens you check exactly where the sweet spot is, and there are many apps now on the Android store or iPhone store which can do this calculation for you, where you input your lens and what camera you're using, and it'll calculate for you the sort of sweet spot for how much depth of field you want. So shutter speed is kind of the simplest one to wrap one's head around. Basically, it's how much you're exposing your sensor to light. So faster shutter speeds, obviously, you're freezing motion and you're freezing the image more perfectly, and the slower shutter speeds, where you're going to have blurs and motion blurs and things involved. So obviously with photogrammetry, you want to have as crisp an image as possible, so you want to eliminate motion blur. Now, if you're on a tripod, it doesn't matter quite so much what your shutter speed is, because you're on a steady platform, and it can be as slow as you like. If you're doing it handheld, it depends on how steady your hands are. The rule of thumb is that whatever your focal length is, you should have that as your shutter speed. So if you're using a 50mm lens, you should be able to comfortably take a sharp image at 1/50th of a second. And if you're using a 100mm lens, 1/100th of a second. With modern cameras, they tend to have shake reduction inbuilt, so you have a bit of leeway on either side, but typically use whatever your focal length is. And then lastly, ISO. So here we have a comparison of what a noiseless ISO 100, which is the sort of base level ISO, would be, and what an ISO 3200 image is. And you can see that one has a lot of noise, which is effectively false information, because the sensor isn't receiving enough light to be able to accurately calculate how the image should look. So it's basically getting false information. So with photogrammetry, false information in an image will translate to false information in the 3D model. So you want to avoid having any false information, or as little false information as possible. So as a general rule, always stick to ISO 100 as your ISO sensitivity. And these three aspects of photography basically play into what's called the exposure triangle, where basically they're playing off one another. And in photogrammetry, it's the exposure triangle is somewhat easy to understand because two of the aspects are fixed. So your ISO is always at 100 and your aperture is generally about f5.6 or f8. Now that's those are quite slow settings. So you need to, generally it's good practice to always bring a tripod along with you, because your shutter speed, which is your one variable, is always going to be quite slow, depending on the light. In museum conditions, it's often quite easy to mitigate that because they tend to have rather good lighting conditions and you can control the light very well. But when you're outside recording a building, for example, this is way beyond your control. So you need to carefully plan your recording session and try to keep an eye on the weather, basically, because even a cloud passing over the sun, it makes the light from the sun more diffuse, which is a good thing, but at the same time, it also makes everything much darker. So you have to slow your shutter speed right down. And basically all of this is in order to get a well-exposed image. And what I mean by a well-exposed image is that in an ideal world anyway, your highlights and your shadows are, you're receiving information from both. So in this slide, you can see in the image on the left, the way the light passes through the aperture, then the shutter, and then finally hits the sensor. Well, basically, you need to balance your ISO, aperture, and shutter speed in order to get a nice balance between the three. So you want to avoid things being too dark because then you're losing information in the shadow in the darker areas of the image. You simultaneously want to avoid it being overexposed because then you're losing information in the brighter parts of the image. And as a general rule, it's better to slightly underexpose rather than overexpose because shadow information is actually easier to recover in post-processing than highlight information. But you always want to try and make life easier for yourself and have the correct exposure for every single image. And in photogrammetry, you also want to have it be fairly harmonious. So you don't want to have like a huge jump between your exposures between images. So if you have an image which is incredibly bright and then an image that's incredibly dark, these aren't going to go well together in the software. This slide is about dynamic range. So, and also I'll talk a little bit about why we recommend shooting raw images over JPEG images. So every camera has a dynamic range, which is the ability to recover information from the highlights and the shadows. So in the image on the left, you can see that there's a huge amount of contrast between the highlights and the shadows, and that it's been fixed in the image on the right, where you can see that detail has been recovered from both. In general, any recovered information is going to have quite a lot of noise, but it's better to have some information than none. So especially when you're recording outside and you obviously can't control the weather, sometimes you just have to make do with the light that you have. And for this reason, it's always better to shoot raw, because with raw images, these details are much more recoverable than with JPEG images. JPEG images tend to be pretty fixed. And so you'll be unable to recover as much of the information that you've lost in the highlights and shadows as with raw. So as I said, shooting raw is very important. And yet I am constantly surprised by the number of sort of professionals I encounter who only shoot in JPEG. For us, actually, the raw is in a way more important than the processed model that you get at the end of the process, because from the raw images, it's always possible to reprocess the data again and again. And for us, it's much better to always record with raw, because not only is your dynamic range better, but raws keep a lot better than JPEGs do. So JPEGs relatively quickly tend to degrade. So for example, I've got JPEG images on some of my older hard drives that are completely unusable as images now. and that's just to do with the way that they're stored. Additionally, with RAWs, your edits are not destructive. You can always go back to the original state, and that's because a RAW file isn't really an image. A RAW file is basically like a data dump of the sensor readouts on the camera, which is then translated into an image by your RAW editing software. So I tend to actually try and for additional protection, convert my RAWs into a DNG RAW format, which is Adobe's proprietary RAW format, because each camera brand has its own RAW format. And this, depending on how committed they are to it, or how well the camera company happens to be doing, there is a likelihood that even this will become unreadable at a certain point in the future. So there are camera RAW formats from camera companies that have gone out of business that are now completely unreadable. But by converting them to DNGs, which is somewhat more universal, I'm able to basically mitigate against that. So even if the company that my camera belongs to goes out of business, I'll still be able to read my files further down the line. So in terms of equipment, we generally recommend using a full frame camera with a minimum resolution of 12 megapixels, which isn't too much these days. I think the standard is about 24. It doesn't particularly matter if it's DSLR or mirrorless, as long as it has the required resolution. We recommend generally a fixed 50mm lens because that's sort of our standard and is a sort of good jack of all trades lens. Tripod, as I mentioned, because your exposure times are often very slow. A physical reference or a ruler of some kind, because photogrammetry is standalone amongst all of the most 3D recording technologies in that it doesn't have an inherent sense of scale. So you have to manually input it. Or you can combine it with another data set from, say, a LiDAR scanner in order to impart a sense of scale. The laptop or desktop computer that you need, basically it can be anything as long as it has a graphics card capable of what's called CUDA processing. Essentially any good gaming laptop, for example, will be capable of doing photogrammetry. A hard drive, usually about 1 terabyte, because you're shooting a lot of photos. That does add up in terms of storage space. You need your photogrammetry processing software. So we have a partnership with Reality Capture, who, in our opinion, are the best of the photogrammetry processing softwares out there. There are others, such as Agisoft Photoscan and Agisoft Metashape, and there's a bunch of free open source ones. A Reality Capture for us is a good sort of is very fast, and it's very high resolution, and we can very seamlessly mix other data sets in, and also it has a sort of, well, we have licensed copies of Reality Capture, but for the average sort of enthusiast, let's say, it has a sort of pay per input model where to process the model, it's completely free. And it's only when you're happy with it that you can pay a sum of about, let's say, 20 euros to export your model. So it's very convenient for people just getting into photogrammetry or learning photogrammetry, because a lot of the other softwares are either incredibly slow or they cost an arm and a leg. And finally, you need a RAW converter. Again, there are many options on the open market, many of them free. Indeed, most camera companies have proprietary RAW converters. My only issue with them is that they tend to be quite slow. So my personal equipment, which is sort of what Factum's equipment is largely based on, is a Canon R5, which is a 46 megapixel camera with a set of sort of wide angle 50mm and then telephoto lenses And yeah, we have in-house calibrated scale rulers, which are basically targets that are known targets to reality capture software. So reality capture can recognize the targets on the scale rulers, and I can then just define the distance between those two targets. So my laptop is a high-end gaming laptop essentially, and then I have a custom-made desktop which can handle the heavier processing. I always carry a color checker passport, which becomes very important for color calibration and color management. So generally speaking, you'll always need to color calibrate your images at some stage in the process in order to get accurate color information, which is always important for the digital output. And then I have reality capture, and I use Adobe Lightroom as my raw converter. So when it comes to capturing the images, it's the main rule is that you should always have about 60% overlap between your images. So 60% of those of any two images will be the same. And the reason why is that allows that gives a good amount of features for the software to then extract, to basically pair together and determine the point of the point in space. So here I have an example of sort of the correct and incorrect way to record a building. So because you're nothing, well, very rarely are things completely rectangular or flat. You have to always account for oblique angles. So you should generally, if you're recording something large scale like a building, pair up triple up your images to basically cover oblique angles on the building. And then you want to increase your overlap by basically double over a corner. And that's because corners are where the process can, or the sort of triangulation between the two faces can come apart. So corners, it's important to have more overlap on your corners so the whole model is captured. Having just one image, as on the bottom here, it's likely to cause problems because there aren't enough features detected on either side of the corner for each section to be joined to each other. So the other important thing is to always have make sure your images are in focus. So I shouldn't really need to say like what counts as being in focus, but basically the image on the right is how your images should look, and the image on the left is to be avoided or deleted. Basically, the software can actually recognize these out of focus images, but it returns a lot of false information from them because not everything is sharp. And basically what it's doing is where it's detecting features such as these sort of cracks on the hand. As you can see in the out of focus image, they're barely visible. So it won't return good information. So you should generally try and keep every photograph in focus, or delete any photographs that are out of focus. Next, you need to have an image, at least 3 images of your scale ruler, or whatever you're using to scale your image, in focus and sort of seen in its entirety. And this I usually do at the beginning of the shoot, where I basically take photographs of the entire object as a whole, because then that basically provides the overall geometry, and then you move closer in, adding detail. And it's a convenient thing to do at the same time as to add the scale in. So especially when you're recording something like a building, which generally have quite complex geometries, it's good to have a lot of consistency. So try as much as you can to sort of have to shoot each image at a predefined distance from the previous image. So it's best not to eyeball it, because that leads to sort of some images having more overlap and some less. You want to have it as uniform as possible. And the last thing I would add is to do with sort of recording setup is that when you're using a flash, basically you should generally try and avoid it because it tends to cast rather harsh shadows, especially if it's direct and not bounced. But also a lot of the objects that we record are quite reflective. So the Cellini bell, which Carlos was talking about earlier, was a very good example of this. Being silver, it was highly reflective, and so we had to use something called cross polarization, where we polarized both the lens and the flash, but in different orientations, so that they cancelled each other out and the glare was minimized. This is can be quite complex, and so I don't cover it until sort of much later on in the training course. But basically, yeah, flashes are, unless you know how to control the light, try and avoid using them. And finally, it's just to periodically check what you're doing. So basically, when I'm shooting, I tend to shoot both RAW and JPEG, and I use the camera JPEGs to basically just check periodically what it is that I'm doing, how is it looking, is it, am I missing any areas, do I need to pay more attention to somewhere, or what have you. Most of the work that we do, we only tend to get one shot at recording it, so you have to make sure that what you're doing is good, because the last thing you want is to get back to the office and realize that you're missing a whole section of a model. So I just want to play this quick video. This is my sort of the project that's been dominating my life for the last 2 years, no, year and a half. And this is in the town of Alula in Saudi Arabia, where we've been recording this 10 square kilometer area filled with Nabatean tombs, which are these rock cut tombs. The 3D models you'll see in this video are they haven't been color calibrated yet, so there's a bit of discrepancy in the color information, but it shows you sort of kind of how we work.
Sorry, Otto, was it supposed to have a sound?
It has some music, but I don't think it's entirely necessary.
Okay, because we don't hear it, by the way.
Sorry, yeah. So as in that video, what you saw there was basically a very large scale digitization of a very large area. And there it's been necessary to do both photogrammetry from the ground and also from the air using drones to capture the sort of images from the angles that are not visible from the ground. And then combining those with LiDAR scans to basically create an accurate scale, as well as to add GPS coordinates into the 3D models. And what these are going to be used for is basically to monitor the state of the tombs and to basically monitor their existing progress, especially as the site opens up to increasing numbers of tourists. So with that particular project, there are a vast number of images and there are 3 different teams doing the recording. And so things like file organization become incredibly important. And overall, it's something that you have to basically do each and every time. Try to have as uniform file structure as possible, because often the person processing the data may not be the same person who recorded the data. And it's quite easy to get lost in just a mountain of photographs. So everything has to be very clearly labeled in order for it to make sense. So the way that we structure it, or the way that we found to be the most easy way of structuring it and the most easily understandable, people may have their own, is basically to have the overall project name followed by the object or building in question. And then within that folder, you have an imports folder where you basically put your raw photographs listed as their focal lengths that they were recorded with and the specific section of that tomb, for example. And here where we've put, like, so for example, room J, wall E, it's always best to either have these things clearly defined using a plan, or to, if you don't have that, name them by cardinal directions. So east wall, north wall. A lot of people I see tend to at first label things as left and right, or somewhat subjective directions, which are not all that helpful. And then finally, you have your exports folder, which contains your digital, whatever your output from the processing software is. So that's your 3D models, your depth maps, your renders, what have you. And then finally, a save folder for your session save. Actually, after you've fully exported all of the 3D information that you need for that project, it's actually best to get rid of this, because if you have the raws, you can always reprocess it and it doesn't take too much effort. But the save file takes up a lot of space, and as the software upgrades, they become less and less usable. But for us, the important thing is to always keep the raw images beyond anything else, because from there, you can do the whole project again, if need be. So the first step to the processing is obviously to develop your raws. Now, theoretically, you should always have, your photos shouldn't need that much editing because you've exposed them correctly and lit them well. But, such as life, things very rarely turn out that way. And so you tend to need to adjust exposures a little bit, or recover shadow information, or take out highlight information, and so on and so forth. This is quite a labor-intensive thing because you have to go through each photo one by one doing it. Occasionally you can copy settings, but for the most part, everything has to be done on an individual basis. And once you're done doing this, you export the JPEGs. You convert the raws you export JPEGs from the raws, and this is what you use to create the scan. So you import your photographs into Reality Capture, for example, or Agisoft, or whatever software you're using, and you align them. Essentially, this is the same process across all of the software. The just depend on how much manual input you have to have. So here we have, this is the example I'm using is a terracotta maquette by Canova, which is in Bassano del Grappa. And it's a maquette of his Three Graces sculpture, which I scanned about 5 years ago. And so what the software does, it goes through each image and it detects a set number, or it detects a number of features per image. How many features it detects depends on your computer and what you've set the upper threshold to be. So, for example, on my computer, I have it set to an upper threshold of 80,000 detected features per image as my upper threshold. So any more than that, and I find things become too clogged up, too slow, even though technically it's possible to detect way more than this. And the more features you detect per image, the better your alignment will be. But 80,000 is enough for our purposes, and it's a nice balanced area where my computer runs at a decent speed and is able to process them. So the image on the left actually displays the process a little better. So having detected the features, it then pairs up those features between the images, and that's how it calculates the three-dimensional model. So each feature detected between any two images becomes a triangulated point. And that's effectively what this model in the middle is made up of. This is what's called a sparse point cloud of millions of measured points that have been extracted from the images. And these blue lines emanating between the image thumbnails, basically illustrating how it's interacting with the images that are surrounding it. So this one image here in the center is connecting to dozens of other images around it. Having done your alignments, it's quite a convenient time at this point in the process to add the scale, assuming you're not combining it with anything else to give it scale. So here, for example, you take the scale ruler, and this particular project was done several years ago, and we now have calibrated targets which are automatically detected. But back when we were using these scale rulers, you had to manually place the control point yourself. So what we did, and what you can still do, is you basically zoom into the image and try to set the point as carefully as you can in the center of this target, and then do the same for the other end of the ruler, draw a line between them, and tell the software this is a known measurement of, in this case, 50 centimeters, and then it scales the model accordingly. So having scaled it, having aligned it, you're then going to turn it from a point cloud into a 3D model. And the way that this is done is basically it calculates a triangle to occupy the space between any 3 points. The reason why it's a triangle is this is the simplest polygon that exists, and actually you can describe pretty much any shape in the universe using triangles. So here we have again the maquette of the Three Graces. This is as a triangulated, was known as a triangulated mesh, a 3D model. And here you have a very zoomed in image of an area. I can't remember exactly where, but this is illustrating the triangulation. So you can see that the entire model is made up of millions of these little triangles. And this is actually how you communicate the size of the model to other people. So typically, in say a video game, for example, a 1 million polygon model would be counted as a very, very high detailed model. As a reference, typically the models that we create at Factum are you know, in the hundreds of millions of polygons. And this is actually too much for most software to be able to handle with computing as it is currently. So we always have to simplify our models depending on the export. The one exception to this is when we're exporting depth maps, which Carlos was explaining earlier, where basically you're not limited by polygon count. And so you can actually export much higher resolution files using depth maps than you can with models. But this isn't always applicable. So in the case of this maquette, if you're wanting to 3D output it, you have no option but to do so as a 3D model in order to 3D print it. So this particular model, we generally have to decimate it down from whatever number it is, let's say 400 million triangles, down to roughly 10 million triangles. And then it becomes somewhat easier to manage. Your computer won't crash when you try and import it into the 3D printing software. And so this, for example, is the 10 million polygon 3D model. This is a very quick turntable where I show it as with and without its color texture. And this is basically in the case of this model, the final 3D output. So this is the file that was then sent to be 3D printed. And just to give you a sense of the resolution that I managed to achieve for this model, we were able to find one of Canova's fingerprints in some of the clay where he must have pressed his thumb to create the shape. And so having exported your 3D model in whatever formats, you then, it depends on what your final output is, where you go next. So in this case, we were asked to make a facsimile of the maquette. And so here we have Juan Carlos in our studio, basically taking a cast from the SLA printed model. And you have two examples of a sort of, well, before he's done with the color, but you have two intermediate examples of the facsimile. And a newer sort of usage for the 3D data that we've recorded is, and which will be spoken about, I think, in another lecture, is in using computer game engines. So using Unreal Engine, we've been experimenting with some of our older projects to try and create interactive walkthroughs. And photogrammetry is particularly good for this, because photogrammetry, as it's become better and better, has been adopted more and more by the video games industry, because they've basically realized it's a fantastic way of creating assets. And so it's something we're looking at as well, in creating much more high resolution experiences digitally, because one of the sort of main bottlenecks in displaying the data has been that the means of displaying it haven't caught up with the ability of the processing software to create the size of model. So typically the only way previously that we've had to show our digital assets to clients has been to show them either a video render, which they themselves can't manipulate, or to upload a very low resolution model onto platforms like Sketchfab, for example, which they can then manipulate, but it's not representative of the actual quality of the 3D model. So trying to use game engines to fully display the quality of 3D model that we're getting without having to physically reproduce it has been, photogrammetry has played a big part in. And that is the end of the presentation.
Thank you very much. Really interesting. I don't see any questions yet. I remember to people attending that you can type your question in the chat on Zoom or on YouTube as well, and otherwise ask talk. I would like to ask Otto a question about the scale rulers. So you showed you've shown the scales next to a sculptor. And what about when you are photographing a building, for example? How does it work?
So yeah, we basically scan the building twice. So we do it once with photogrammetry and also with a LiDAR scanner, which is basically a surveying tool. So it basically measures using lasers and measuring the time it takes to bounce back to the scanner. And that has an inbuilt scale in the 3D data. The other way that you can do it is using GPS coordinates, but this depends on how accurate your GPS receiver is. So when you're flying a drone, for example, the drone has a GPS receiver inside, and you can use that data to scale the object, but it tends to be accurate to about 10 centimeters, which for our purposes, it often isn't good enough.
Okay, I see. So for usually you use just photogrammetry for smaller objects, and you combine LiDAR and photogrammetry for architecture, for example.
Yeah, so specifically with architecture, photogrammetry is more for capturing areas that need high detail, because obviously I'm not going to record like the tomb at a distance of 50 centimeters, because that would just be millions of photographs and no one could process it. So you economize by basically recording color very generally with photogrammetry, because LiDAR color tends to be quite bad. And then using the LiDAR as the general geometry and the scale, and then you focus on particular parts of interest on the buildings to have a more detailed model in that area.
Clear, thanks.
I would like to try to show something, if there are no questions for now. If there is any question, please let me know, Costanza.
Sure, not yet.
I would like to build on something that Otto mentioned. I would like to comment. I will share my screen now. I would like to comment, especially I would like to hear Otto's comments, because this is, I don't know if you can see on the screen now, I'm rotating this 3D model. In the next session, we will be talking about ways of disseminating 3D information, ways of allowing access to the digital recordings. And what Otto mentioned about using video games engines in order to facilitate, for example, an interactive experience through in a virtual environment, for example, that can keep the real detail and the real quality of the recordings, is something that we are literally now trying to find the best way to do it. So we will cover a bit of that in the next session, but what we have today, and one of the most available tools, is these platforms like Sketchfab, in which you can upload your 3D models. But obviously, what you are uploading is a simplified version and a decimated version of the real model that you have, because in order to be able to show this information on real time on the screen, you cannot really upload the maximum polygon count that you maybe have been able to capture in a proper recording.
Yeah, you can actually hide. So in this particular example on Sketchfab, you hide the fact that it's a low polygon model with the texture, which is again something that the video games industry does a lot. So here the color information, this is actually the cross-polarized color information, hence why it looks gold when the actual object is silver. So the parts of the color where it looks black are actually where we were getting reflections, and basically by cancelling out that reflection, it looks black in the image. So this is actually before the color has been corrected. But basically, this is a very low polygon count model, but the texture is, you know, an amalgamation of all of these high resolution images that we've taken. So the texture is high resolution. The texture is on this, I believe, a 4K resolution. Maybe it's 8K resolution, actually, which means that you can use it to sort of hide the fact that it's a low polygon model. But for us, the surface information is more interesting. Hence, we like to decimate the model as little as possible.
And even taking into account that Sketchfab is one of the platforms that you can use, and you, of course, have to simplify your model. Even with simplifying it, you can see the amount of 3D information that it's included in a model like this. And when you are showing the information with the color, what is normally called the texture or the color texture, is a way of hiding maybe a too simple 3D model. But because we are interested in the capability of reproducing this thing physically, we want to be able to record something that is valid for both digital output and material output. So when someone is showing you a 3D model with the color information, I think it's important to ask to see it without the color. So you will be able to really understand what's the amount of effective information that you have in your 3D data.
I think you mentioned before, now Otto said the black or darker parts are the parts in which there were more reflections, and maybe you mentioned before that to avoid that this reflection, this glossiness would ruin the pictures. Did you use a polar filter? Is it correct? Did I hear well?
So yeah, you have a polarizing filter in one orientation. Well, it can be either horizontally or vertically over the lens, and then a polarizing filter over the flash in the opposite orientation to what it is on the lens. And that basically allows you to basically polarize the light coming from the flash and the light being received by the lens. And that basically allows you to somewhat eliminate specular highlights caused by the reflective nature of the object. It's not perfect because it tends to make the highlights go black, which is also a loss of information, but it reveals more information than if you were just directly flashing the object. And it also makes the color go a bit weird, hence why this looks gold rather than silver.
There is thank you anyway. There is a question by Diego Perez regarding photogrammetry and small objects. Is it better to take photos moving the camera around the object, or let the subject rotate on a small platform and standing still with a tripod?
Either is valid. Actually, if you want to be very precise about things, it's better to have it on a turntable. The only thing that you have to be aware of if you're doing that is you have to completely isolate the object from the background. So you need to have some sort of featureless cloth or something as the background, because the photogrammetry does also align using the background information. But provided you've isolated the background, it's actually somewhat more precise to use a turntable, which is what we did with the bell.
Okay, that was pretty small, as we have seen the 3D model. Yeah. Thank you.
I think I see a question in the chat. From Maria Hanso. Saying, what kind of application do you use to combine and match data from the LiDAR and the photogrammetry? Actually, you do it in the photogrammetry software. So you have to process the LiDAR within its own software, and you have to export what's called an E57 file, which is a structured point cloud, essentially. And then you import that folder into Reality Capture or Agisoft or whatever your software is. And then you align it to the photogrammetry in the same way that you would with additional photographs.
We can't hear you, Costanza.
Sorry. I was saying that I invite again people to ask their questions if they have some now, because otherwise I think if you don't have anything to add more than this, we can say goodbye.
Very well. Thank you everyone again for attending, and thank you Costanza for making this possible.
Thank you. Very interesting as usual.
Thank you. See you next
Have a
time.
nice evening.
Thank you.
Bye.